linear transformation of Gaussian random variables. Let us say x1, x2 up to xn, they are jointly Gaussian and random variables. Now we get the output equations as y1 up to yn, they are linearly dependent on the input equations. The constants are a1, a2 up to an. Now if we describe this linear equations in the matrix form, we get this. These are the output equations. This is the constant. These constants are described in a matrix. This is called transformation matrix. This is the input equation. Now y is equal to tx. If we according to linearity proportion, we can also describe this as x is equal to t inverse of y. Now if we go to the t inverse matrix, only the t inverse matrix is the input equation. Only the constants will be changed. All the remaining will be same. X bar, the input equation, can be also described in form of output. This one is the T inverse matrix. Now if we describe this T inverse matrix in the linear equation form, we get this. According to the Jacobian rule, if we differentiate each and every element with its respective random variable, we get the same constant. So that's why we can describe this in as Jacobian matrix. Now this is the Jacobian matrix. This Jacobian matrix is directly dependent to the T inverse matrix. So according to the, if we take determinant on both sides, we can get mod Jacobian is equal to T inverse of determinant. Now mod J is equal to 1 by T determinant. Now we can discuss about covariance matrix. Covariance means if we have n random variables, then we can take the covariance of n random variable. Covariance is nothing but the expected value of the random variables minus its mean value. Now if we solve this, we can get the covariance of x is equal to T inverse, the transform matrix inverse, into the output covariance matrix into the transform matrix inverse of transpose. Now from which we can, by this relation we can also get, by doing inverse on both sides, we can get covariance inverse is equal to T transpose of covariance of y inverse into transform matrix. From this we can get this. Now if we find the determinant of covariant matrix, inverse of covariant X matrix, we can get this. This transpose of T and the T, both the determinants are same, so we can get T square determinant here. Now according to the Gaussian random variable jointly density function, we know that the Gaussian jointly density function is 1 by 2 pi n by 2 covariance of x inverse 1 by 2 exponential of x, the random variable matrix, minus its expected mean matrix transpose of covariance x inverse of x minus x bar matrix divided by 2. Now we want the equation in terms of y. We want to transform this density x random variable into y random variable. Now we should replace this. We should see that covariance of x and covariance of x inverse, we should replace it with covariance of y. Now if we replace with by equation 1 and 2, here we see that from equation 1 we got the from this equation we get the cx and cy inverse relation. Now if we put the cx and cy relation in this cx inverse and cy relation, we get the output relation as this. Thank you.